Assalamu alaikum dear students. Welcome to the lecture of the classical mechanics. In this lecture, we will solve the solution for the problem number 7.3, which says that a sphere of radius rho. This is a sphere of radius rho is constrained to roll without slipping on the lower half of the inner surface of a hollow cylinder of radius r. This is the cylinder. This lower half is radius r. This is the cylinder as we are talking about, and this is the sphere of radius rho. This radius is rho. This radius is rho, and we have to determine the Lagrange function. First, we have to find the Lagrangian for this and the equation of the constraint. Okay, and the Lagrange equation of motions. Find the frequency of small oscillation, as it's you know that if this body will come its lower position here, it will not stop due to inertia. It will go on the other sides, and again it will come down and start to and fro motion, which will be like a simple harmonic motion. Means we have to prove that this motion is simple harmonic, and then we need to find out the frequency of that small oscillation. So let's go to its solutions. The first thing is that if we try to find out that what are the constraints that are acting and that are impeding in the body motion. So the first thing is that this r theta, this angular displacement will be equal to r theta. So this curved path r theta, r minus, mean its effective radius is r minus r. Its effective radius will be equal to r minus this r, this rho. You know that this we can represent this by rho r small r. So r minus r into theta minus r phi should be equal to 0. This is the constraint, because this constraint is that this disk should not deform. This disk should not deform. Then it's r minus r into theta minus r into phi should be equal to 0, because if we consider this disk as a solid disk, so this will not deform, and this r minus small r into theta minus r phi should be equal to 0. This is the constraint which are acting on this body motions. So let's go. The first is kinetic of energy of the rolling sphere will be equal to, because our body is sliding and also rotating, so we will have kinetic energy is equal to m over 2 into v square and plus 1 by 2 I, you know that omega square. So translation and rotation kinetic energy, you know that with this is equal to r omega, and omega can be written as theta dot, and this r is r not equal to r, but its effective radius will be equal to r minus r, because we have to find the distance from the center to this radius as this one, this radius r minus r. This will be the effective radius of the particle motions, so it will be equal to r minus r, effective radius of this particle. So kinetic energy will be equal to m over 2 v square, which is equal to r omega. So r minus r into theta dot square plus 1 by 2 I, and omega is equal to phi dot. So its square will be equal to phi dot square. So 1 by 2 I phi dot square. This is kinetic energy of the particle, which is simply the summation of both the rotational and translational kinetic energy of the sphere. Where the potential energy, you know that potential energy is equal to mgh. Potential energy is equal to mgh. What is h? H is the, you know that the height from the ground, which is equal to r plus r minus r into cos phi. You can find the h from the diagram. Is this body come down, that you know that for example if it comes at this point, so we will resolve its weight into two parts. This radian into r sine phi and r cos phi. R cos phi. If we know this, the total distance is r minus r, so this will be the r sin phi, and this will be r cos phi. So if we try to find out, this will be equal to total r plus r minus r into cos phi. Here I have made a little mistake. If I want to clear it, so this will be that this distance is r minus r. So if its body come here at this position, it will be r minus r, and if we try to resolve this in two components, so this will be equal to r minus r sin phi, and this will be equal to r minus r sin phi. That this total distance is equal to capital R, and this distance is r minus r sin phi. So our height is actually this. So if we subtract this total r from r minus r sin phi, we will get this height. So actually our h is the height of the body is equal to mg, which is equal to r plus r minus r into cos theta, where r is the radius of the sphere, and that this is the solid sphere, so its moment of inertia is equal to 2 over 5 r square is the rotational inertia of the sphere. So Lagrangian is equal to T minus u. We have kinetic energy. We will put the expression for the kinetic energy, and then minus potential energy, and then for equation of motions, because we have two variables theta and phi, so our Lagrangian equation will be equal to one for theta and one for phi. So du partial L partial theta minus d over dt partial L partial theta plus lambda partial f over partial theta is equal to 0, and partial L over partial phi minus d over dt partial L over partial phi dot plus lambda. This f is the equation of the constraint. We have already found out this, and we will just put this. Lagrangian is given, so we will put Lagrangian here, and also we will put Lagrangian at this point. I will take derivative with respect to theta dot as the usual method of algebra, and then partial f over partial theta, we know f. This is the value of f. That equation of constraint f is equal to r minus r theta minus r phi. So we will first differentiate with respect to theta, then with respect to phi, and then put in these equations. We'll put in these equations, this and this will give equation of motion for equation of motion for two variables, the first for theta and the second for phi. So if we evaluate this, then this solving for the parameter lambda, we got lambda is equal to minus 2 over 5 m r square phi dot. Also from the constraint we have lambda is equal to minus 2 over 5 m r minus r theta dot double dot. Therefore combining the two equations, theta double dot will be equal to minus 5g over 7 r minus r sin theta. If theta is small, then this sin theta can be written as theta. So we will have simple harmonic motion, means that theta dot is proportional to theta, and this minus sign, it means this is simple harmonic motion, and the other constant will be omega square. So this is omega square. Omega square is equal to 5g over 7 into r minus r, and omega will be equal to its under root. So this is the frequency of the system in the case of small oscillations. And just the difficult thing is it's Lagrangian. If you find out the Lagrangian, it means there is nothing difficult with it.